Okay. All right. Good afternoon. I think that we're at this time of the semester that the real work is going to start. Really? Real work. Trying to exactly. Ultimately, what this class is all about is doing design and not just analysis and things like that. So that's exactly what projects are all about, is kind of coming up with a problem that has no explicit answer, and it's up to you to come up with the right answer, or as good as possible, something which is the best. And as I said, there might be many good answers to the problem. That's typical for any design problem. So that's what we're going to do today. Okay, I was expecting that. So a couple of things. Number one is homework 5 is due on Monday. Now, homework 6, we're not going to post it today. Give you a little bit more leeway. It's going to be posted on Monday. So you don't have to start working it over the weekend. You have already worked enough with the project. Labs are done. We're almost over. So make sure that any missing report is turned in as soon as possible. In a week's time, we're going to actually start freezing the grade on that about a week from now. Okay. And we launched the project today. I changed things on the website. Remember the little missing links? It was because of the fact there's 2 words. It's like lecture 13, and sometimes I only change the 13, sometimes I only change the lecture. So that's what happened with copy and paste. So that's all fixed. All right, so let's talk about the project. The project is going to be about, as I mentioned last lecture, is going to be about memory. That's really what it's all about. It's designing a memory. And the following thing is basically what we're going to go after. On-chip memory is a big component of every chip today, and I think we discussed this earlier. You look at a microprocessor, 75% of the transistors are devoted to memory. Okay? Now, the chances that a memory is going to work correctly, if you have, let's say, 700 million transistors, the chance that your memory is going to work all the time correctly is hard. And number 2, it is a good chance that during the operation, while you're basically operating your chip, occasionally you might get a failure in memory as well. There's a couple of reasons why that is, right? Obviously, there's some manufacturing problems. If I have 700 million transistors, there's a good chance that some transistors might be bad. Now, with memory, that's not too hard to deal with, because when you get your chip back from the fab, what I can do is test it. And if there's certain areas that are corrupted, I can exclude them. Like you do with the disk, for instance. If you buy a disk today, 1 gigabyte disk or something, don't believe that all the bits on those disks are working. So they do a test and they exclude certain sections of the memory of the disk which are not working. Now we can do this on chips as well with memories. You take some rows, you take some columns, you say, boy, there's an error in there, I'm going to exclude that. So we can do that. So manufacturing errors are something we can deal with. The problems are harder with errors that occur occasionally. Things that we are calling now soft errors. They're not hard. It's not because it fails that it's going to fail forever. It fails one time and then might work again. And one of the main culprits of those things is what's called a alpha particle, and other things are basically neutrons. Actually, it was around the late 1970s that people designed the first DRAMs, and they saw that something occasionally was going wrong. It was an error happening in memories. And they did simulation and simulation. I couldn't figure out where it was coming from. So at some point in time, people were ready to give up on DRAMs. Within Intel, there was the 4000 and whatever, 4K memory approximately at that time, 4 kilobits. Till somebody figured it out. It says, you know, in the package where you put your chip in has certain plastics. And these plastics tend to emit occasionally high velocity particles called alpha particles. They're emitted by some kind of radioactive. Now, don't think about major style radioactive, that basically a chip is going to make you sick or something like that. But there's some radioactivity, and some components degrade over time and emit particles. And these particles hit a memory bit, they can make it flip from one position to the other one. So that they discovered that, and they said, okay, now we know how to deal with that. If I make the capacitance on a given node large enough, and I'll show you in a second how you do that, then I can avoid that flipping effect to happen. In other words, if I have enough charge on a node, it's hard to flip it around. But we make things smaller and smaller and smaller. Right? It means that getting enough capacitance is getting harder and harder and harder. So the critical, or the charge we can store, is stored on a memory node, is getting smaller. Another thing that basically starts happening is another particle, which is neutrons. Neutrons are basically everywhere. They kind of go, you don't notice them, they fly through it, but if they by accident just go into your memory and hit the bit, it flips. And people have shown this, for instance. If you take, let's say, an FPGA, and you run it here in San Jose for a number of weeks and things like that, you might measure a certain amount of errors happening, or for years. They do this analysis. You go to Denver, your chip doesn't work as good. So never move to Denver, because your processor might fail more often. And it's just the fact that you're at a higher altitude, way up higher there, the density of the number of particles that basically make it through there is a lot more, because they don't have that much reflection and protection. So neutrons are another big part. So how to deal with this? There's two options. If I make my cells bigger again, put a bigger capacitor there, obviously you're going to have less of those errors. Right? But that defeats the purpose. I'm scaling technology to get more bits, not less. So this is something that's not very effective and something we don't like doing. So the other option is to let errors happen. So okay, what the heck, right? Maybe once a day or once a week, a bit is going to flip. If we can detect that a bit is flipping and we can correct it, then we're fine. So we add some error correction to it, like we do in wireless communications. We do error correction. Why not do this on memories as well? So we're going to talk about in this project is really about an error-correcting SRAM memory. That's really what we're going to design. But before I go there, let me explain a little bit why soft errors basically happen. So suppose, let's say that I have, in this case what I've drawn is not an SRAM cell, but a DRAM cell. The DRAM cell is really nothing else than a capacitor with a transistor. And this is C, this is called the bit line, and that's the word line. C storage. So the way a DRAM works is by storing charge. Very simple. You have a capacitor. If there's no charge on the capacitor, you have a 0. If there's charge on the capacitor, you have a 1. And the way you read and write that memory is using what's called an access transistor, which is driven by the word line. So when the word line is high, you connect the bit line to the capacitor, and you can charge it or discharge it for the write operation. So if I put a 1 here, I turn on the word line, I charge up the capacitor. So that's the way you write it to a DRAM. The way you read out a DRAM is the same thing. You leave this capacitor, this bit line floating. You pre-charge it to some value, maybe VDD over 2 or maybe VDD, that doesn't matter. And then I turn on the word line. If there's no charge, if there's charge stored in this capacitor, this is at VDD, and I pre-charge VDD, nothing happens. Right? You have VDD on the capacitor, and you have VDD on the bit line. You turn the switch, you close the switch, nothing happens. However, when there's this 0, when there's no charge on this capacitor, you will see that I'm going to take some charge from this capacitor and feed it and store it on this capacitor. You do charge sharing between the two capacitors. Net effect is that the voltage of the bit line, which is at VDD, is going to drop a little bit. Because you have charge redistribution, your voltage is going to drop a little bit, and then I use an amplifier to detect that. Right? It's the basic idea of a DRAM in a nutshell. This obviously is very small. For a single bit, I need 1 transistor and 1 capacitor. Okay? And that's kind of the cell what I've drawn here. You have the bit line, which could be metal, diffusion, and things like that. The word line is polysilicon. That's our transistor right here. And here you have your capacitor. And I just showed an example here of a capacitor that's implemented in diffusion. But you could do other things as well. Actually, it's typically not done that way. It's typically done a lot more complex than this. But bottom line is that I have here somewhere a capacitor with some charge on it. Charge or non-charge. Now, suppose that by accident a alpha particle wanders through. This is a high energy particle, comes in out of space, or whatever it is, and hits your chip. it goes into the substrate. It basically goes right to, and it goes into the substrate. And what these particles do is generate a bunch of electron hole pairs. So you get all those electron hole pairs that basically are being generated. Now, some of those might just recombine again. If an electron finds another hole, they recombine and disappear, nothing happens. Some of them don't. And as you can see, suppose there's a positive charge here stored on my capacitor. And I start collecting a bunch of electrons. Because of the voltage, electrons get attracted to that charge trap. They eliminate some of those holes. You can see that the value of that's stored on that capacitor is going to change. You change the charge on the capacitor. How many of the electrons basically really go to change the capacitor value? That's what we call the efficiency. Well, efficient is not the right word. It should better be inefficiency, because you don't want to have that efficiency. But you can see that the more you basically collect, the more chances you have that basically things get disrupted. So as I said, what you really want to make sure is that you have enough charge stored on your capacitor so that when the particle hits that you don't really get impacted. Or you make sure that the efficiency of the collection is low. If most of the electron hole pairs don't make it to your capacitor, you're going to be fine as well. Okay? So you have to think about special architectures that basically minimize that efficiency factor. Now, this used to be only a problem in DRAMs. DRAMs were very sensitive to this. Turns out that SRAMs have the same problem now as well. SRAMs, as you know, and as we briefly discussed before, and we're going to talk a lot more about this later in the semester, an SRAM is nothing else than a cross-coupled inverter pair. Okay, so you have a value stored, another value stored here. That's our SRAM. It's basically an inverter cross-coupled with another inverter. That's an SRAM cell. And these things tend to be bistable. They either go in one state or the other state. Again, I'm not going to go more detail. So, in principle, this is static. It means if you disrupt some of the charge here, it might restore it. That used to be the case. Now, if I, however, start making, you have to think about the capacitance here. There's capacitance on these nodes. If I now start injecting a lot of charge on one of those nodes, by, for instance, having an alpha particle, it actually might make this inverter pair flip from one side to the other side as well. So SRAMs are also now vulnerable to soft errors. And you will see that if you go to the most advanced memory chips today, people start adding error correction on it. So error correction is something which we didn't used to do. We only used to do them for DRAMs. We definitely do them for non-volatiles. Every flash memory has error correction on it because of the fact that the more you read and write it, you get some degradation. So if you want to increase the number of read and write cycles in a flash memory, you use error correction. But SRAMs is really the newest thing. So how does this work? Well, here's the memory we're going to consider in this project. It's a 1K by 4K memory, which is 4 million bits. Not a staggering number, but a decent-sized memory. At least decent-sized memory block. As we discussed before, a typical memory, SRAM memory, consists of an address, which in this case we have 1,000 bits. That's going to be 10 bits. Actually, it goes from A4 to A13. 10 bits basically gives you 1,000 rows. This goes to a row decoder, and from 10 bits we go to 1,024 values, only one of which is high at any point in time. That's the word lines. This selects a row in your memory, and every row is 4,096. Now, in this project, we like to have the data stored as chunks of 64 bits. Let's say this for a 64-bit processor. Right? So they're stored in 64 bits, but you don't want to have a memory of let's say it would be 16,000 or even a lot more, very long, skinny 64-bit memory. Now we put a number of the 64-bit words together in one single row. Actually, we put exactly, this is not correct, this 4 should be right here. It's actually 64 by 64, which makes exactly 4,096. So in every row, I have 64 of those words stored. Now when you read all those 4,000 bits out, and then the column decoder is going to pick the right 64 out of that, what you're reading out. So we have a column decoder that basically takes 4,000 bits and creates 64 bits at the output. Actually, this drawing puts the sense amplifiers before the column decoder. Actually, in the real implementation, you're going to put it behind it for an SRAM.
The online project description is right.
That's correct. Yes, this is the old drawing. Because if you look at this, don't worry about sense amplifiers yet. We're not going to meddle around with those yet, but we'll come to that later. What they do is take that small signal that comes out of the memory bit. You have a little tiny memory cell sitting there that tries to drive a big capacitance. Because you look at the single column, we have 1,024 cells on the single column. So you can imagine that the capacitance that sits there is huge. And then you have this tiny little memory cell tries to flip that bit around. You know that's hard. So what we do is you say, well, I'll let that tiny little bit do what it does. We're going to create a small signal change, and then we put an amplifier behind it to magnify that change and turn it into a real 0 and 1. But in this case, like if I draw it here, I would need 4,000 sense amplifiers. Sense amplifiers are power hungry. They're big. So rather what I'm going to do is take the SRAM, take the column decoder, and put the sense amplifiers behind it. In this way, I can reduce the number of sense amplifiers from 4,096 to 64 only. It's a lot cheaper from an energy perspective. We'll redraw that, and it's definitely drawn correctly in the handout, which is, by the way, already posted on the website. Okay? So that's the traditional way. But this is error-prone. So what we're going to do, well, what we do is the following thing. Behind this is actually drawn correctly. What we're going to do is you take a 64-bit word. What error correction does is, well, in order to make sure that errors don't happen or that we can correct errors, we're going to add some redundancy. If I take 64 bits, I'm not going to store 64 bits, but 64 bits plus k, where k is a given number that we're going to have to figure out. We call those parity bits. You add the number of parity bits to it. So there's redundancy. And if you add a lot of redundancy, depending upon the amount of redundancy you add, you can correct or detect a number of errors, and you can correct a number of errors. Now, detection is easier than correction. If you want to correct them, you're going to need more parity bits than if you want to only detect it. Sometimes it says, okay, this is wrong. But that's pretty useless. Very often it says, this is wrong, and I have corrected it for you. This is now the correct result. Sorry? Now, this is going to, I will explain in a second what the whole story is, what we're going to use, what code we're going to use in this project. So 64 plus k, bits you store. So this is now, instead of 96, it's going to be 64 plus k times 64. So we're adding 64k bits to the memory. Make it a little bit, there's redundancy, but it buys us some. Then, these bits are coming out of our, when I do a readout, goes to the column decoder, goes to the amplifier, I get 64 plus k bits. We feed this through a decoder. The decoder is going to look at the 64 plus k bits and detect if there's an error and where that error happens. In the other case, actually, we're going to use Hamming codes. Hamming codes are the simplest codes around. They were detected, people already had those, what do you call it, invented quite a while ago. Out of this comes an error bit location. It says bit number 7 is wrong. So then, obviously, you want to do correction as well. If I know bit 7 wrong, then I have to flip that bit back and put it in a normal position. Okay? So what we're going to do in this phase of the project is to design this part as phase 1. No memory, no decoders or anything like that. We're just going to assume that we have 64 plus k bits coming in. And I want to get out of there 64 correct bits, independent of if the word was wrong or correct. We're going to design a code that detects only one single error. Okay? Not 2 errors in a row. The probability that you're going to have 2 errors in one row simultaneously is going to be very small, because the probability of software is already very small, and a very small makes very, very, very small. So we're going to do only 1-bit correction and detection. Okay? And as I said, we're going to use the Hamming code. So let's basically explain what the Hamming codes are a little bit. Well, like any code, there's a variety of code. There's iterative code, there's turbo codes. You've heard about all those type of things. Hamming codes is one of the simplest ones. It's a block code, basically. And what it does is the following thing. It adds, as I said, a number of parity bits. Like here, you have your word. This is a very simple example of a 4-bit word. 4 bits plus k, and k in this case is 3. I'll explain you why we get to 3 in a second. But you see that you have bit 3, bit 5, bit 6, bit 7 are normal data bits, and P1, P2, and P4 are parity bits. Okay? Now, if a word is correct, there's a number of checksums we're going to create. Checks. We basically XOR P1 with a well-defined set of bits, like in this case B3, B5, B7. Okay? P2 gets XORed with some other bits in our word, B3, B6, B7. And which fraction, that's exactly defined about how you basically construct the code. And P4, B5, B6, B7 is another checksum. So in this case, we have 3 parity bits. We have 3 checks to do. Each of them takes 4 bits as an input. Okay? Now, so as you can see, this is basically nothing else than a 4-bit XOR function. So we have 3 4-bit XORs to perform. If there's nothing wrong, if the word is correct, we're going to see that the checksum should be all 0. Okay? Now, however, if suppose that one of those bits might go wrong, let's say B5 goes wrong. Bit 5 has an error in it. It has flipped. So what we're going to see is B5 is right here and right here. If we just flip B5 around and we do the XORs, we'll see that we find this particular code. Right, this bit, this parity check stays 0. This goes to 1. This goes to 1. Now look at what I got here. This is the number 5. Actually says bit 5 is wrong. So you know exactly the bit position out of that process. Take another example. Bit 3 goes wrong. Then we're going to have 1, 1, 0. Basically says position 3. So this Hamming decoder tells me what the, if you have everything zeros, you're fine. If there's 1, 1 in there, you have a problem. 1 bit is going to be wrong, and we're going to have to correct it. Yes?
How do we know that the XOR is going to return 1 or 0? If there is an error.
Well, if there's no error, so this code, by the way, when you write the data into the memory, first of all, you're going to choose your parity bits, right? The parity bits has to be chosen by the encoder. Before you write it into the memory, you're going to carefully select P1, P2, and P4 in such a way that when everything is correct, you get 0, 0, 0. Okay? Now, when an error happens, you feed it out. You always go to the decoder, right? All zeros, we don't have to do anything. If, however, I detect there's at least one 1 in there, we have an error. And we know how to detect it, because if there's only one single error, we can use that code to say, hey, flip bit 3 or flip bit 5, and your word is going to be correct again. Okay? So that's the way it works. Now, this thing corrects 1 error out of 4 bits. Yes?
If there was an error in the parity bits.
If you assume that there's the hardware, or the error in the parity bits, they will also show you errors, but it's not going to be one of those particular words that you're basically going to see happening. So yeah, if your parity bits go wrong, you're also going to be seeing some flipping around, but this is going to be, as you will see, it will be showing only, there's actually 1 extra bit that you will see here. There's actually 4 checks you can do. This is actually not within the realm of things. It's going to correct the parity bit. Yes?
So are the parity bits stored in the SRAM? Or?
Yes. So if you think about it, every 64 bits on a word, we're going to add k bits. And you can see the parity bits are all stored at, they're kind of not separated. They're not at the back of the word or at the beginning of the word. Actually, they're intermingled. And they are positions 1, every power of 2, basically. 2 to the 0, 2 to the 1, 2 to the second, 2 to the third, 2 to the fourth, and so on and so forth. Now, as I said, to correct one error in 4 bits, what this example shows, you need 3 parity bits. Now, how do I know this? Well, there actually is an equation. The equation says that for Hamming codes to work, to correct one error, you have to basically obey the following equation. 2 to the k has to be larger than k plus n plus 1. Okay? Where k is the original number, where n is the original number of bits, in our case would be 64, and k is the number of parity bits. So k has to be chosen in such a way that it meets this equation. Now let's look at the example of 4 bits. 4 bits. Here it is. Now suppose k has to be larger than, 2 to the power k has to be larger than k plus 5. What is the smallest number of k that meets that requirement? That's really what you have to think about. If I would choose 2 bits only, I get 4 is definitely smaller than 7. So 2 bits don't do. If I do 3 bits, you get 8 is larger or equal than 8, exactly right. So 3 bits are fine. So let's think about how many we need for 64 bits. So now I have 2 to the power k larger or equal than k plus 65. What do you think will I have to choose for k? 7. That's right. So k, 2 to the 7 is 128, is larger than 72. Clearly, 6 wouldn't do, because that would give us 64 is definitely not larger than 71. So it has to be 7 bits. So in our case here, a single word is now going to be extended to from 64 bits to 71 bits. I get 71 bits coming out of the memory, and I have to feed in my decoder and my corrector to get the output. So this is really what we're going to focus on in this project, the design of this block. Okay? And I'm going to make it easy. Easy. It's, number one, only static CMOS. We haven't seen anything other yet, so this is going to be your traditional static complementary CMOS gates. No dynamic logic, no other things you could use to cheat and become faster. Static CMOS. We're not going to do layout. Really, there's an effort in optimization. So what I require you to do is design all the logic for this thing and minimize the critical path in its length. And the options you have, obviously, is how you construct the logic, but also especially how do you size the transistors. So this is going to be a major effort in logical effort optimization, the type of thing we've gone through. You have to figure out what the critical path is, where it belongs, and there's some constraints as well. The constraints, obviously, is looking into my N-sense amplifier. I don't want to have a big load. So we say that the maximum load you can have is 4C, looking into the input. And C is the input capacitance of a minimum size inverter. So you can have a load which is 4 times C. Now this output probably is going to go to some latches or something like that. So we say that the load is also not big, it's also going to be 4C. 4C at the input, 4C output capacitive load as well. Not much fan-out. The real problem is going to be sitting in fan-out factors here internally, and how you design this thing. So that's really what we're trying to do here. So first thing you do is you look at the problem, start playing around with different schematic diagrams. What's the logic you would use? And then you can imagine already here 64 plus k parity bits. You're going to start with some XORs, right? Because Hamming code decoder, this thing is a bunch of XORs. And how many input bits do we have? We can know that too, right? 7 input bits. But I'm not going to say anything more than that. The rest is for you to basically figure out.
How do you implement XOR?
Static CMOS. Yep, no pass transistors allowed. So this is going to be pure static CMOS. So if you need inversion, you're going to have to implement an inverter. No choice about it. There's no avoiding. But you will see that you will see that it might come out quite nicely, actually. So let's see. So static CMOS. So the first thing you do your logic, and then you do kind of play around with logical effort. How many stages do you need? Where do you need more stages? Does it make sense to insert buffers in certain cases? Use more stages, less stages, all these kind of things you can play around with. The bottom line is that I want to minimize, assume that all those bits are available at the same time, and I'm looking at the worst bit at the output. So then what you do is put it in Spice, and you want to convince me, number one, is that your thing works. I'm going to give you actually a number of patterns that you should simulate, and it shows if I make an error in my bit, it should come out correct at the output. So you have to prove that your logic works. And then the second thing is, given the fact that you say, here's my critical path, you simulate the critical path and figure out what the worst case delay is. Okay? So no layout required. This is purely schematic level design. Later on, when we do other blocks of this design, we're obviously going to do layout. Because I just can tell you in phase 2, we're going to design the decoder of this thing. And there I'm going to do layout, real layout. In area is going to be a factor. And later on, we're going to do this fraction here, column decoders and sense amplifiers. So we're going to go to all phases of this design. So the only thing we'll not let you do is basically the SRAM cell. We'll give you an SRAM cell that you can use. Because doing a good SRAM cell takes quite a little bit of tricky kind of layouts, type compression. You want to make your cell obviously as small as possible. So area of the cell is very important. Okay? So that's the idea. Now a couple of other things. This project is done in groups, not on your own. You basically can have groups of 2. So try to find the first thing you have to do, the hardest part is find a good partner to work with. It's only, I'm not sure exactly how many, if the number of students in the class is odd or even, depends. I have to think about exactly where we are right now. It's only in extreme cases, and if you want to do it all on your own, you think, boy, I'm way better off on my own. Partners only slow me down. You have to come to me and have to have an explicit type of approval. In this case, groups of 3 do not make much sense. Typically in projects, they say if you want to be a group of 3, you have to do 3 halves of the work. You have to do more work. And I don't allow, in this case, there's no more work to be done. So groups of 3 are not going to be allowed. So if there are an odd number of students in the class, we should be able to do this with groups of all 2. If there's an odd one, then we have a little problem. Then there has to be at least one group of 1. Or in the exceptional case, I'll see. We'll figure it out when things happen. So the way the output of this thing is you have 3 weeks time. It's due Monday after spring break. So for those of you who plan to stay around here for spring break, it's a good opportunity. For those of you who are gone, that's too bad. So 3 weeks, and what I get out of this is a report. I just need a report, and you will see the report is very structured. I hate reading reports of 75 pages on a small project. So it's going to be a 3 to 4 pager where you have different spaces to fill in certain parts of your results and how you come to your results, what patterns you use, what do you think the critical path is, and so on and so forth. Okay? That's basically it. This is going to be fun. I think this is a real nice optimization project. And I think in this case, this is one of the easier ones because I believe there's a unique solution, or a pretty close to a unique solution to this. There's not going to be many variants. If you start doing the other parts, you can see there's a lot more variants coming into the game. Okay? Any questions? Good. So it should be clear. Yeah, so things are posted on the website. All the information is there. You can start rolling. And by the way, this is 90 nanometer technology. And by the way, also, you're not allowed to run the thing at 15 volts. The supply voltage is max. I believe David, it's 1 volt, right? 1 volt max. So no trick like say, hey, I'm going to use 5 volts. It's running faster at 5 volts. Doesn't work. So maximum 5 volts. You can go lower than that, but I wouldn't advise it because it's going to slow you down. Okay. All right. So that's summarizing what we said. Find a partner, derive the schematics, prove that it works, using only static CMOS gates. Worst case delayed by transistor sizing and topology, obviously. But the topology, you already kind of divided together with this here. And report the critical path delay as is obtained by spectra and prove with a simulation to me that this is your critical path. I want to see the numbers. I want to see a waveform in the end that shows, here's my critical path that I simulated, and lo and behold, this is TP right there. Okay? And report by Monday, March the 30th. Okay? Alrighty. Good. So let's now go back to power dissipation. So we did the inverter. We've discussed all the type of tricks we can use to basically make the thing fast, how to get the propagation delay, simplify the analysis. We've done all that stuff. So let's talk a little bit about power dissipation. There's not much to be, in terms of power dissipation, there's actually, if you look at the CMOS inverter, we have given you so far this equation, right? The power dissipation you're going to consume is CV squared. Right? If I flip an inverter around, CV squared goes on my supply, and CV squared over 2 gets dissipated in the first part of the action, and CV squared over 2 gets dissipated in the second transition before we're back. So we have a full transition from 0 high to a high to low. We consume basically CV squared. Now, that's not the complete story. There's only one part of the story. It's what we call switching power, dynamic power, charging and discharging capacitors. That takes energy. Now, this is not the only one. There's actually other sources of energy dissipation in CMOS inverters that you should be aware of. Number one, short circuit power. Short circuit power is the fact that our crossbar current, as some other people call it, is a current that happens when I have a finite slope, not a step function, but I have a finite slope that I apply to an inverter at its input. There will be a certain period of time that my PMOS and NMOS are going to be on simultaneously. And current will flow directly from VDD to ground without charging the capacitor. That's a loss factor. That's extra power dissipation. We don't want that. We try to keep this as small as possible because it's a waste. It doesn't help us to charge the capacitor, so it slows us down. And it basically goes to the drain. Literally. You lose it. So that's a big source. And then there's another source of power that we didn't used to worry about. Something that said, hey, we're CMOS, complementary CMOS, we don't have to worry about its leakage current, leakage power. The fact that if I don't do anything, one of the beauties of CMOS, or at least originally of CMOS, is if you don't do anything, you don't consume any power. It just sits there. Your PMOS is off and your NMOS is on, or your NMOS is off and the PMOS is on. But never both at the same time, so if you don't do anything, there's no current flowing, you have zero dissipation. Now, unfortunately, that's not the case anymore. Things leak. Transistors are leaky valves. And there's current flowing in them even though when you think they're off. And that's getting worse. So leakage power is something that only came an issue later in the 1990s, and now today is a big, big issue. Which is obviously a problem, right? If you have a cell phone, can you imagine you don't do anything and your battery drains while you're not doing anything? That's not a good thing to have. Finally, there's a last source of power dissipation in CMOS that could happen is static currents. Like in analog, if you have an analog circuit, you need bias currents. Every amplifier needs to be biased. Bias currents are DC currents. They always flow. Means that that amplifier is going to consume power continuously, even though it doesn't amplify anything. In digital logic, we have less of that, but it's unavoidable. Occasionally, I need an amplifier. Remember the memory I just talked about? We have sense amplifiers. Sense amplifiers are amplifiers. It means they have a bias current. Bias current basically creates steady-state current, steady-state power. So that's something that we have to be aware of, but most of the time in logic, we won't have any of that. We don't want to have any of it. Logic that uses static current is a really bad idea. And you're going to have to work really hard to convince me that it's a good idea. Okay? Because I don't think it's affordable. Unless you have only one gate that is like that. Sorry? Shoot for an overprime, but I don't think you will get it. Try hard, try hard. I think if you make a gate that has a standby current of about 1 atto ampere or something like that, what's below attos? It's zeta. Is it zeta amps? Something like that. 10 to the minus 21. What is that? Zeta? Iota? No, I think it's zetas first. So it's atto, and then I think it's zeta. But I have to check it out again. Okay. So let's go briefly to the different sources. As I said, I'm not going to tell you very much anymore about the dynamic power dissipation. It's fairly straightforward. Every time I switch an inverter from 0 to 1, I take CLVD squared of the supply, and half of this goes to the PMOS, half of them is going to be distributed in the NMOS and the discharge phase. Okay? That's all we really have to care about. Now, in terms of power, this is energy. Power is energy multiplied by the frequency of occurrence. Right? So, in order to find the power, we find the energy per transition, and I'm only caring about 0 to 1 transition, because if you look at it, at least in the simplified format that I showed you before, with all the capacitance shown as capacitance to ground, as in a simplified model, CLVD squared is consumed when I have an up transition from 0 to 1. Then I take CLVD squared out of my supply. When I have a 1 to 0 transition, I don't do anything. I just take the charge from the capacitor and dump it to ground. So what the power dissipation is going to be CLVD squared multiplied times the frequency of the 0 to 1 transitions. Okay? Now, what's that? This is one of the hardest problems. In terms of performance, if we want to compute performance, we know what the critical path is, we simulate the critical path, we're done. Right? That makes analysis for performance quite easy. Well, quite easy is not the right word. It might take some effort, but it's quite easy. Now the transitions, you can see F01 here is this transition periodicity is a function not only of the logic you have, but also of the what we call here the probability of a 0-1 transition to happen, which is going to be a function of your data. Suppose I have a microprocessor or a data pod, and I only apply zeros to it. Right? And my only inputs are zeros, and I keep it at 0 all the time. I don't change it. There's going to be no power either. Right? So the power dissipation is going to be a function of the switching probability, which is data dependent. Right? I can use different data patterns. I apply to my logic, I will get different power dissipation numbers than when I basically have another data pattern. And very often the worst case type of thing you could do is take random data. People very often simulate a block by throwing random data at it. You take a random number generator and you simulate the thing through a number of cycles and say that's my average power dissipation. But that's the worst case because random data makes things flip and back and forth very often. If you have, for instance, arithmetic, very often it happens that the MSBs, the most significant bits, flip far less often than the LSBs. The LSBs is a noise, right? The MSBs is kind of, if you have like a sine wave, something that, a sine wave, you will see that the LSBs are flipping every transition, but the MSBs change very, very, very slowly. So in this case, your power is going to be lower than when you would have random data. Okay? So power dissipation is equal to, now, that's kind of a pain. This F01, I like to have let's say when I have a synchronous circuit, I would like to express my power as a function of the clock frequency. Right? F is the clock frequency. So the power dissipation would be CLVDD squared times F, but then I have multiplied this with an active factor, which is the probability that on a clock transition, I will have a data transition. That's alpha 0 to 1. It's the probability that on a clock transition, my data will change. Okay? So that's an important number, and the only way to find that number for a given node is probably simulation. Now, you can do some tricks. We'll talk about it later. You can try to do intelligent stuff, but your intelligent stuff goes real bad real quickly. It basically becomes very complex if you just do more than 4 or 5 gates. So most of the time what you do is you take a high-level simulation, you feed your data to it, maybe at Verilog or VGL level, you simulate the thing, brrr, you look at all the transitions, you say, okay, the average number of transitions is going to be this. And that's what you're going to use in this equation. What people very often do is multiply alpha 0 to 1 and CL. So CL is the actual physical capacitance, but if I multiply the physical capacitance with the probability that switch, we call it the switched capacitance. Kind of, then you can say my power is VDD squared times F times the switched capacitance. The average capacitance I'm going to switch around on every transition at an average capacitance. And that's given by this expression here. Okay? This is exactly the same thing. I don't know why I left this slide in here. It does exactly the thing. It basically says what you do is you count the number of transitions, number of 0 to 1 transition. If you take a long number of them and you take the number of 0 to 1 transition over the number of cycles, you get alpha. Bingo. That's fairly straightforward. Okay? So that's what I wanted to talk about. Dynamic power, fairly easy to find. By the way, if you run in SPICE or Spectre, and Spectre, you know how to find propagation delays, right? You look at the 50% point at the start, 50% point at the other waveform. You actually have some very simple commands in SPICE that allow you to do this automatically. You have dot measure commands that says measure the 50% point from this, 50% point here, bingo, you get the results. And it gives you the propagation delay in one shot. You don't even have to look at the waveforms. So dot measure allows you to do propagation delay outputs quite easily. There's also the command in SPICE which allows you to do average. So or integrals. It allows you to integrate the energy that basically flows or the current that flows to a certain thing over a certain period of time. And obviously if you do that and you multiply this with V, you will get the power dissipation. So SPICE actually allows you to measure power dissipation quite easily. Over a period T, you say, okay, here's my period T. I'm going to integrate my current over that period of time. I basically get the integrated current, multiply with the voltage, and I have my power. Okay? Now, so that's source number one. Let's talk about short circuit currents. And turns out that, as I mentioned, short circuit current, let me use the overhead camera. Okay, suppose I have an inverter. Here. And instead of having my input as a step, which basically turns off the PMOS or the NMOS instantaneously, I'm going to apply a slope factor. Okay? Then you see from the time you basically are above VTN and below VDD minus VTP, both PMOS and NMOS are going to be on simultaneously. Right? So there's going to be current flowing from VDD to ground, and we have power dissipation. Now, here's now the key question. Suppose now that I would like to minimize that short circuit current. Right? That's my goal. Right? I don't like short circuit current. It's a waste. Let's try to figure out how to minimize it. Well, I can do some trick. Let's try to figure out what's happening if I change my load capacitance here. Suppose, for instance, I make CL really large. Make it huge. Absolutely huge. Make it infinitely large. What's going to happen with the short circuit current? I have a fixed slope at the input, and I make my load capacitance infinitely large. Really, 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 really big. What do you think is going to happen with your short circuit current? Will I have a lot of it? Will I have less of it? What do you think? Remember, initially this thing sits at VDD, right? That's the initial position. What do you think the contribution of short circuit is going to be in this particular case? And this assume that this is close to infinity. No guess? It's going to be large or small? There's only two choices, right? Small. Why would it be small? What's happening when the capacitor is infinitely big? What's happening with the output? No. Definitely not floating. Oh, loading. It's loading. It's definitely loading. But what's going to happen with VDD? How fast will it move? It won't move at all. It's infinite capacitance. There's no way I can make it move. So this stays at VDD. This node, so what short circuit, basically, I turn this on. I'm basically going to this period here. I turn on the NMOS. But the PMOS, basically the VDS of the PMOS stays at, over this thing here, since this stays at VDD, this is at VDD, you have 0 voltage over the PMOS device. Nothing current, if you have 0 voltage, no current will flow through it. So actually your short circuit current is going to be 0. This is typically the case. When I actually make the output slope very slow compared to the input slope, I'm going to actually consume quite, because before we really get through it, this thing will never really have a lot of current flowing through it. Okay? Now, let's do the opposite example. Let's take, again, my inverter. Yes.
Don't you get a longer delay if you have the output slope really long?
Absolutely. So it's good for short circuit current. I was coming to that. This thing is obviously very good for short circuit current, but it's absolutely awful because it doesn't do anything. Right? It sits there forever. It's an infinite capacitance. So it's extremely slow. So it's not something I really like from a performance perspective, but from a short circuit perspective, it's really cool. So let's do the same thing now, but same waveform at the input. And now I'm going to eliminate this capacitor. I'm going to set CL equal to 0. Okay? What's going to happen in this case in terms of short circuit current? It's going to be maximized. Because what's happening is a single leg, suppose you have no load capacity whatsoever. There's always intrinsic capacity, but assume you have 0. You turn this NMOS on, a single electron comes by, switches your gate from one to the other one, and it maximizes the voltage over your transistor. Bingo. PMOS will basically sitting there dumping current, doing nothing else. So large, really fast. This gate is going to be extremely fast. Actually, we'll have a negative propagation delay. Right? If you think about it, you have a slope. You can look at 50% point. The output goes like this. You have a negative propagation delay. But the short circuit current is very big. Now, I cannot build this because in reality, I always have capacitance. Right? So, the problem what we can conclude out of this is that making your load capacitance larger or making your output slope slower than the input slope helps to reduce short circuit current. If I make the output slope faster than the input slope, I'm going to have a boost in short circuit current. Now, this one is bad for performance, so we don't want to have that. So like always, what we do is compromise. So, okay, I want to get good performance and low short circuit current. What should we do? Well, we compromise between the two. And a good compromise is that if I can make the input slope of my gate approximately equal to the output slope, that I don't have a very big deterioration, or if I want to make sure that my output is not moving too fast compared to my input, you're going to be fine. This is what some people call slope engineering. You want to make sure that your slopes in your circuit are kind of all of the same type of nature. You don't want to have a signal that's really, really, really slow in there. Because if you use that to drive the next gate, that gate is going to have a lot of current flowing through it, short circuit current. So if you design your circuit in such a way that your slope factor, that your slopes are basically identical for input and output, the max amount of current that's going to go, or power that's going to go into short circuit current is about 5%. I'm willing to pay that. 5% is a small number, so that's what we live with. Larger than that is not very good. Okay, 3 to 5% is what I can play around with, and the way you do that is by using slope engineering. So if I go back to my figure here, you can see that this actually plots the short circuit current for various values of the load capacitance. You can see if the load capacitance is very large, 500 femtofarad, you get a fairly small short circuit current. And the smaller I make my capacitance, the larger my short circuit current becomes, as we basically discussed. And that's the result of SPICE. But as I said, the short circuit current we can control nicely by controlling the slopes of the signal. Okay, so that's source number 2. Let's go to source number 3, leakage. Again, let's look at our transistor inverter. Okay, so where does leakage come from? We already know that drain and source region of your transistor, and especially the drain region here, is an inverse bias diode. Right? In typical operation, if you don't go out to the supply rails, this is a reverse bias diode. Now, what we know about the diode is that, if you remember that, a diode has a current dependency is something like this, right? So when you turn it on, suddenly the current goes zoom. But in reverse bias, you see there's a current flowing, but it's a very small current. But there's a current flowing. So that means that even if, let's say, suppose this sits at VDD here, we will have some current flowing through our diode in this particular case. So if VDD, this is, let's suppose this is an NMOS device. For an NMOS device, you look at in this case, this is at VDD. Now this is for the ground factor. In this case, the PMOS won't leak very much, but the NMOS will leak. If this is at 0, the PMOS will basically leak, and the NMOS won't leak very much. Because it's at 0, it's at this particular point here. You don't have that much leakage. But bottom line is, you cannot avoid diodes. Diodes are always going to be there. They're always going to leak. The good news is that the leakage current is very small. We're talking less, fractions or basically range of picoamps, which is very small. And in general, we're not going to worry too much about that. So, yes, leakage is there from the reverse bias diodes, but I'm not going to worry too much about this. There's only one thing that you have to be aware of, is that when you start heating up your chip, you make it warmer, you kind of power dissipation, you're in this big data center, you make it flip back and forth, you dissipate a lot of heat. Temperature goes from room temperature to about 90 degrees Celsius or something like that, or 80 degrees Celsius. What's going to happen is that your leakage is going to increase substantially, because you know that the diode reverse current is a strong function of temperature. Actually, it doubles for every 9 degrees Celsius. Temperature goes 9 degrees, leakage current goes up with a factor of 2. So you have to be aware of that. You go from 30 degrees to 90 degrees, huge difference in leakage. And then it might become a little bit more important. But anyhow, this is not the dominant source of power dissipation, static power dissipation. There's another one, which is more important. Transistors that are supposed to be off actually do leak. The fact is that if this device here, let's say you have VDD in here, so supposedly this is at 0 volt, the PMOS is off, you would expect no current, but in reality there's going to be subthreshold current. And the same thing in the other situation, when the output is high, the NMOS is leaking and current flows through it. Now, why is that the case? Well, I mentioned this already before, but if you look at your transistor, let's say NPN, and your gate, well, you see that obviously when we have a voltage, V gate applied, which is smaller than the threshold voltage, I won't have a channel. There's no conducting channel. So the transistor is literally off. But as I've shown in this picture here, what we have is that this NPN forms a bipolar transistor. The bipolar transistor is kind of weird because the base of the bipolar transistor is not directly connected to the gate, but to a capacitor. So the voltage that I'm going to apply right here is going to be kind of a capacitive divider between the gate and the substrate. Okay? And that's going to determine how this current basically flows. Now, for any of you who has basically ever heard about a bipolar transistor, you know there's one thing which is an important property of bipolar compared to an MOS transistor. What would that be?
Base current.
Yes, what's true about the base current? Yes, it's base current, that's fine. That's true. But in this case, we have a gate which is isolated. I'm not worried about that. What's the most important thing about a bipolar transistor, which is different than a MOS transistor? Exponential current. So the current is an exponential factor of the voltage, the BE I'm applying, VBE. Which means that when I start basically dropping my gate voltage, we'll see an exponential dependency in my drain to source current. And this is shown right here. This plots the IDS of my transistor as a function of VGS for one particular value of VDS. So you see that when VGS is fairly large, we have a quadratic or linear dependency. But once we get too close to the threshold sitting right here, you see this is going to drop off exponentially. This is an exponential, this is a log linear plot. So the subthreshold current is an exponential current. And it's an exponential current of VGS. So reducing my current below VT, or my voltage below VT, you can see that, yes, I still have a current, but it drops down in an exponential fashion. Okay? So that's always been the case. It's been the case 20 years ago, has been the case 30 years ago, is the case today. So why do we worry about threshold voltages then? Why do we care about leakage current today more than we did in the past? What has changed? Well, it's the following thing. In the good old days, we were operating at VDD of 5 volt, and people were happily operating with threshold voltage of around a volt. But nowadays, for energy purposes, and also because electrical fields, you make things smaller and smaller and smaller, I have to scale supply voltage. If I scale supply voltage and I don't scale threshold voltage, what do you get? Worse performance. Right? Remember the ID sat? ID sat is equal to K times VDD minus VTH. Or VD sat, VD star if you want to. Doesn't matter. So if I reduce VDD, I'm going to get less current. It's going to have a direct impact on my performance. So what do? We scaled the threshold voltages as well. We made them smaller and smaller and smaller. 0.6, 0.5, 0.4, 0.3. Now, what's happening as a result of this? If you look at this curve, by changing the threshold voltages, I'm moving this curve to the left. So something that was, let's do it very simplified. This is for one threshold voltage. For another threshold voltage, I might get something like this. Oh, it's not very well drawn. Let me just move it over here. So what I'm going to get is something like this. Okay? So by moving the threshold voltage, I move this over to the left. But remember, this is exponential. So if you look at the current for VGS equal to 0, that's where my transistor is off. You can see that the current is not equal to, when VGS is equal to 0, you can see that the current is not equal to 0. There's some current flowing. However, if I reduce my threshold voltage, you can see that I get a fairly important impact on the current at VGS equal to 0. So our leakage current has substantially gone up and up and up and up by scaling down your threshold voltages. And we had no choice, because keeping the threshold voltage high, your performance goes down the drain. So we had that challenge, and that's why leakage current has become more and more important, because of the fact that we basically are operating at smaller VDDs and smaller threshold voltages. Okay? But the key factor is drain current is exponential with VGS minus VT. If you're a curious person, here's the equations for it. Actually, they're very similar to the bipolar equations. It's like the ID, the current here, so the current in subthreshold region is, as you can see, in superthreshold, you have linear behavior, this velocity-saturated device. You get closer to the threshold, you get more quadratic. And then you go subthreshold, you get an exponential dependency. Okay? And the equation is like the bipolar equation. It's in the bipolar case, you're going to have IS times over the VBE over KT over Q. For those of you who remember that. Same equation here. ID is equal proportion to I0 times KT over Q, or sorry, VGS minus VT over KT over Q. And KT over Q we call the terminal voltage. Is approximately equal to 25 millivolt at room temperature. Okay? There's one extra factor that comes in here, this factor N. N is actually showing the fact that this is not really a bipolar transistor because there's a capacitive divider in there. So the drive of my bipolar device is not via VBE is going to be determined by that capacitive divider, which is CD, the diffusion capacitance, over the oxide capacitance. Right? So N is going to make this a lousy bipolar transistor. It's not really a good bipolar transistor, but it's a lousy one. So you have to have that extra N factor N, and N sitting around typically between, around 2-ish. Somewhere between 1 and 2 approximately. It's rare that it's going to be above 2. Now, some people don't like exponentials. They like more like powers of 10. It's easier to think about it. So there's another definition of N. It's actually a direct relation of N. It's called S. And S is expressed as N times KT over Q times ln 10. It's really when I express the current as a function of power of 10 instead of an exponential. Okay. Now, S is a very interesting thing to remember. S is, suppose I'm here. I turn my transistor off, and I get a certain current. What S basically expresses, suppose now that I want to reduce my current with a factor of 10, right? 1 decade. I want to go from here, which is about 5 to 10 minus 10. I want to go to somewhere up here. What is the reduction in VGS that I need to reduce or enable that reduction of 10 to happen? Okay? So how much do I have to drop VGS to get a reduction of 10 in leakage current? Okay? For an ideal bipolar device, this is 60 millivolt. Okay? You just take this thing here and you put 1 in here. 25 millivolt times ln10 gives you 60 millivolt approximately. So every time suppose my threshold is 0.4 volt, I drop my voltage 60 millivolt below the threshold voltage, my current is going to go down with a factor 10 in a bipolar device. Good. And do another 60 millivolt, I get another factor 10. So if I have 400 millivolt, let's make it easier. Let's make it 360 millivolt. That's 6 times 60 millivolt. Your current is going to go down with a factor 10 to the 6th from where you are in the at the threshold point till you basically go into 0. So that's not bad. That's 1 million in terms of current drop. It means that the leakage current is going to be quite small. Unfortunately, not a single MOS transistor has a subthreshold slope of 60 millivolt. In reality, there's always this N factor. So N varying between 1 and 2, as I mentioned. Typical numbers are about 80 millivolts per decade to 90 millivolts per decade. So the slope is not going to be very steep. It's going to be a little bit more like this as a result. So if I now take, let's say, 90 millivolt, I get only a factor of 10 to the 4th reduction in current. Right, this 364 times 90 is 10 to the 4th reduction. That's a factor of 100 more leakage current. So there's a lot of people working on today. If you go to some of the universities, like here in Berkeley, and you go to MIT and things like that, a lot of people trying to make transistors that have a steeper slope here. How can I make this slope as steep as possible? If I can make it steeper than 60 millivolt, boy, that would be really cool. Some people say it's impossible, but then people have come up with new device structures actually where they got lower than 60 millivolt per decade. I really would like to have a switch like this, right? It goes off and go, bingo, it's off. You would like to have that. Will never happen, but we're all trying. That's what research is all about. Go for the impossible. Good. So, but that's a very important observation, right? That this leakage current is going up and up and up and up and up. And as a result of that, you might say, gee, if I look at this thing here, say, well, gee, I get 10 to the minus 9th, 1 nanoamp of leakage current. Why do you bother? Right? It doesn't matter. Now, nanoamp, 1 volt, that's 1 nanowatt. Who cares, right? However, if you have 1 billion transistors sitting in parallel, you start multiplying this with 10 to the 9, and you have a watt of power sitting there. And in reality, it can be quite larger than that. So leakage current has now become maybe 30% in some of the chips of the power dissipation. If you wouldn't do anything, if you don't do anything to fight it, you might end up with a big fraction of your power dissipation just doing nothing. So that's not a very good idea. And people have been thinking very hard to deal with that. But it's something you should be aware of, that leakage is a result of the subthresholding and is a direct result of the thresholds reduction. This is also the reason that if you look at newer technologies, you go from 90 to 65 nanometer, you look at the thresholds, and they have virtually not changed. And you go from 60 to 45, and the thresholds are flat. We haven't figured out yet anymore how to scale the thresholds further so they keep them flat, which as a result makes it a problem because you don't get as much performance improvement anymore. But we didn't want it anyhow because it caused the power dissipation to go up and you have higher clock frequencies. So they all came in quite handily. Okay? So that's an important thing to remember. This is another effect that you should be aware of. It's the same thing. What I'm plotting now here is ID versus VDS for a given value of VGS. Let's say this is for VGS is equal to 0. Okay? Now, this almost looks like a normal current curve, right? You have your current, you say this linear mode, and then when VDS goes higher, you have kind of a saturation. And yes, there is some effect like diffusion current. There's some effects like body length, channel length modulation, and things like that going on. But the real factor that basically causes the current, you see that this is my leakage current, and what it says is that my leakage current actually goes up substantially. So you have a transistor. I put VGS equal to 0 and I increase VDS. You would expect its current to stay constant. In reality, it goes up substantially. This is an effect which is called DIBBLE, drain-induced barrier lowering, as it's called. It's really the injection of carriers from the drain into the bulk. And that's extra current to the overall picture. And it's kind of annoying, right? If you look at current technologies, going, let's say, between 0 volt and 1.4 volt, or approximately, your current might go up, your leakage current might go up with a factor of 10. So it's a really bad idea to have a transistor like this. This is really not good, because it maximizes the leakage, which is what we would have in a normal inverter anyhow. Okay? So be aware of that. Now, one last factor that I want to bring up, something that's related to the fact that we already have discussed before, is that thresholds are not a constant. They vary, as we discussed last lecture. Now, if my thresholds vary, right, my leakage current is going to vary as well. Actually, my leakage current is going to vary exponentially. It's an exponential function of the threshold variation. That's why you look at modern chips, you can see that you take two chips, like two Intel processors, and you put them next to each other, and you see that the leakage power of one might be substantially larger than the other one because of the exponential effect. Okay? Now, actually, it's worse when we go for very long, very small transistors. Actually, there's an effect that says that if I reduce, let's say I take a transistor, and I look at the threshold voltage as a function, typically we would expect that the threshold voltage is a constant, right? We expect that. Threshold is something that's given to you. And the only way to change is with the body source voltage. Actually, it turns out there's some other ways to play around with the threshold. It's changing the channel length. When I make my channel length smaller and smaller and smaller, you can see that you have certain depletion region around it, right? The smaller I make, this depletion region kind of eats into your overall channel, basically makes the amount of channel they have to turn on, the amount of charge I have to provide, makes it smaller. So you might expect that the threshold voltage itself is going to be somewhat of a function of the channel length. And it is. Actually, the channel length, basically, the threshold is something like this. When you go to very small transistors, your threshold starts to drop, your leakage current is going to go up. Right, so typically digital designers like speed. They don't care about all of the other stuff. They like energy dissipation. So digital designers typically always use minimum size L. There's no reason to make a transistor with a longer L. While analog designers like to do all the kind of weird shapes of W's and L's and all this type of thing. Digital designers are very simplistic. They say, nope, every transistor, make it as fast as you can, make it as small capacity as you can. So use minimum L. But that comes at a penalty because minimum L, as you can see, has somewhat of a lower threshold. It's good for performance. It's bad for leakage. So that's something you always see as well. The chip that leaks a lot is a really fast chip. So, you never can get both things simultaneously. So if you're really worried about leakage, actually you can design and use somewhat larger transistors. This is very nice timing all the time, right? This battery lasts about exactly an hour and a half. Or no, an hour and 25 minutes. So it is actually perfect. So bottom line there is that channel length, if you want to basically reduce the leakage, you make the transistor a little bit longer, and you can actually reduce leakage to a certain extent. But it increases dynamic power dissipation because your capacitance goes up. So it's a trade-off. All right, so good luck with the project, and we'll see you all next Wednesday. Have a good weekend. Like 4 of them.